Network troubleshooting using Wireshark.
So today what I'm going to cover is a full speed analysis of a packet capture taken as part of an investigation. What I mean by full speed is going through the analysis as if I were doing this in a professional setting for a real problem without necessarily focusing in on one skill. So it is valuable to focus in on skills so that you could understand some theory behind it and actually practice. But it's also valuable to see how things go in the real world so that you can pick up, combinations of different techniques. So what I've done, and I found this post from looks like a Wireshark or wireshark.org. The user has posted a PCAP. They've said, I've been trying to troubleshoot random persistent network problems. I keep running into, was I advised to use Wireshark to capture the network activity to pinpoint where the problems may be happening or coming from. But I'm having trouble understanding and determining what normal activity is to look like through Wireshark and what isn't normal to be able to effectively track down the problematic activity. So the user has posted the file, which I've downloaded. There's one comment here about the fact that the user is using IPv6, and that's the address, and the capture was on their laptop. Now, first thing off the bat, when you are looking to analyze a capture and someone is providing it to you or you're taking it yourself, you should always provide certain pieces of information with that capture. So, pieces of info. Number one, source, dest IP, source and destination IP. This helps you understand the specific application or set of applications which are having issues over the network, as opposed to just looking at things and looking for any obvious problems. Because if you look at any wide open capture, chances are you're going to find a bunch of problems. The question is, which problem is the one the user's having? Number two, description of problem. Is it constant, intermittent, etc.? Right? This helps you in troubleshooting and analyzing the data. Number three, if you have ports, so TCP or UDP ports, if it is TCP or UDP, this is sort of the base set of information that I would always ask. Now, in this case, the user hasn't provided any of that except the IP address, which someone else was able to pull out. So what I'm going to do is go through this capture and try to figure out as many pieces of information I can and take some notes and show you what that looks like. Before we get to the PCAP, just a quick note on capture points. And I've mentioned capture points in the past as well. So in this case, the user has taken the capture on their local machine. That's okay for troubleshooting issues that involve your local machine communicating outbound to some resource, whether it be a resource on your local network, like another PC or another resource or a server, or a resource, say, on another network, which we need a router to access. So usually this, if this was your house, this would be your ISP router to get to the internet. Now, what you're not going to see in this capture is traffic from, say, this PC to the internet, or traffic from this PC to other resources in the LAN. This is because that traffic will not be switched or sent to your PC and your interface. So if, for example, you wanted to capture this PC's traffic, you would want to run a capture on this PC. If you wanted to capture all traffic for all machines going in and out of the network, say to the internet, you would capture on the router. So in this case, we've captured here, so we'll see what we can see from that vantage point. Okay, so the capture is here. Let's see what we can see. Right off the bat, we see a lot of IPv6. IPv6 is not really that common within a local network. I'm not sure if this user has decided to play with IPv6. It doesn't really matter. It's just a different IP scheme of identifying at layer 3, but they've used IPv6. I'm going to do a couple things here just to make this easier for me to read. First of all, I have time delta on. I'm going to turn that off. Second of all, I'm just going to expand this a little bit and go from there. So if I just scroll through, it's always good to start with the scroll through and just get a sense of what you see. Right off the bat, I'm seeing a lot of black packets. In this case, it's TCP, so TCP retransmissions and dupacks. I'm also seeing, oh, that's a lot more of that. Occasionally we see some UDP53, that would be DNS generally. And that seems to continue, those retransmissions. Now, most of this is IPv6. There is some IPv4 as well. If I want to get a sense of the entire capture and what kind of communication is going on, I usually start with statistics conversations. And we'll start with Ethernet. So Ethernet, there are 5 conversations. You can see here the primary one with most bytes is this one here with the MAC address ending in 1524 to 6A02. So the question is, which one of these is the MAC address of the local machine that the capture is taken on? Now, if I go back to the description of the problem, they said that 198E is the MAC address of the local laptop. So there's a couple of ways I can find out what that is. If I go back to the capture, and I'm going to look for a packet with 1980. So here's one right here. Source is this, destination 1980. If I go up, I'm going to pull out layer 2. So this is layer 1, layer 2. Source is this. In this case, this is the destination of this packet. So the destination MAC address, is this here, E60582866802. So I'm going to copy that. Oh, go back. Sorry. We're going to copy value. I'm going to put that on my notepad. Laptop is that. Okay. One piece of information is found. So now if I go back to conversations and I compare my note 6A02, so it looks like the conversation of note that has the most traffic is between my laptop, in this case 6A02, and whatever else this other MAC address is, still to be determined what that is. There's a good amount of packets transferred from A to B as well as B to A, so it's bidirectional, and maybe we can focus in on this. If I look at IPv4, there is some IPv4 traffic. Presumably this machine is actually dual home or has interfaces or adapters for both IPv4 and IPv6. If I want to confirm that, what I can actually do is go back to here, and I'm going to select this MAC address. I'm going to copy this as a filter. You can't really see that in the capture, but let me see if I can do this here. Right click, copy as, oh, still can't see it. Right click, copy as filter. And that creates a filter for you for display. You can pop into the address bar or the display filter bar. And what we could see here is that that MAC address is associated with both the IPv6 conversations here. But if I want to, I can't do that. Let's just look for IPv4. Yeah, right there. Boom. So now we have an IPv4 conversation. Okay. So the address here, the destination is 6A02. That is my destination. And the destination IP address is 192.168.121.9. So let's go to layer 3. Destination. Copy value. You didn't see that on the screen, but just follow through. And IPv4 of laptop is this. And just for argument's sake, I'm going to do the IPv6. I believe this was it. Let me just double check my notes. 1980. I'll just copy it from here. All good. PV6 of laptop is this. Okay. Normally, it'd be nice to have them provide that to you, but they didn't. So there is some IPv4 traffic. There isn't much. I can tell that by just looking at the number of packets overall in IPv4. We knew that the IP address in IPv4 was .9. .9 is featured here. There is some traffic. At least we know that this the laptop is communicating on both. Okay. Now IPv6, here's where you have quite a lot of traffic. And if I'm going to sort it, I usually like to sort it by the number of bytes. And right away we see there's kind of a main conversation here that has the majority of traffic. So my IP address to whatever this is here, 93A1, and then as well as some others. So let's just note that as a conversation of interest. I'm going to prepare as filter. And what prepare as filter does is it copies the filter that you're going to create to the clipboard so you can use it later. So let's do that. Now, we have some TCP conversations as well as some UDP. Right now, I'm not so interested in it. UDP, it looks like there's not much. TCP, there's a lot. Really, I think my focus is probably going to be on this main conversation here. So let's get back to the cap. Now, as I mentioned to you, we see quite a lot of retransmission. And so what I'm going to do is I'm going to focus in on this conversation that I pulled out, which is the conversation that has the most traffic. And I'm going to filter and see what it looks like. And then you can see here there's quite a bit of retransmission on the conversation. The question I have in my mind is where is this destination? Is it a local destination on the LAN, or is it a destination, on the internet somewhere? So there's a couple ways to do that. If I remember correctly, statistics. TCP stream, TCP round trip time. And let's switch direction. Okay, so TCP round trip time will give you an indication of the round trip time between the source and destination. Okay, and this gives you an idea in your head of where this destination would be. Okay, so this is kind of all over the place. It's a bit different or difficult to actually see what it looks like, but it looks like the average is something around 15 milliseconds. Okay. Now, to give you an idea, if you have a local LAN, which is like a switch or like a home modem, and PCs, you should see a round trip time of like 1 to 2 milliseconds most, or at the max. If you see it going beyond 10 to 15, chances are that resource, either it's on the far end of a very, very, very large enterprise network, or it's somewhere on the internet. So my assumption is going to be that this destination is on the internet somewhere, but we can do a few things to kind of validate that and see what it looks like. But that's one trick to kind of help you figure out where that would be. You can also look at the same thing if you pick an acknowledgement coming back from the far end. So in this case, the far end is A1. So what I want to do is I want to find, shrink this a bit, and an ACK packet coming back from A1. So in this case, this is an acknowledgement to A1, but let's see for acknowledgement that is coming back from A1. So this is from A1, it's acknowledging something. So what I can do, I'm going to go down a little bit so I can get some better data, is in the section under TCP, sequence acknowledgement analysis. It's not doing it. Usually it will tell you the time it was acknowledged at, or how long it took to acknowledge that packet before it. Bytes in flight, 93A1. And I'm going to scroll down because sometimes you don't get that because of the time. Okay, we don't have it here, but we'll skip it for now. But I think from that other graph, we can be fairly certain that the round trip is somewhere around 15 milliseconds. We do see retransmissions here at duplicate ACKs, so let's see. I'm going to add to this filter. So, and tcp.analysis.retransmission. So this is going to look for how many retransmissions are there in this total capture. And you can see there's quite a bit. So there are a total of 9,586 packets. Displayed is 3.3%. So roughly 3.3% of the total traffic is retransmitted. As a rule of thumb, there is a whole formula to calculate this, but If you get anywhere up around 2 to 4% retransmission, then you're looking at severe degradation TCP. So my guess is this has something to do with the instability or the issues that user was referencing, because this conversation is the conversation that has the most traffic, and it has almost 3% of packet loss. 4% of packet loss in my book is unusable. It's so bad that you will have significant drops in throughput and issues with most applications. So 3% is pretty bad. So let's try to dig in to see what we can see about that retransmission, because that is certainly a problem. So I'm going to start by looking at these retransmissions right here. All right, so let's see what we can see here. I'm going to try to shrink it a bit because we're using IPv6. The lines get pretty big, and I've made this really big for YouTube, so try to squeeze it a little bit. All right, so here we can see Wireshark tells us that in this conversation, this previous segment was not captured. So this is from 9381 to us, and it's saying the previous segment is not captured. Okay, so what this indicates is that Wireshark is saying, well, I see this segment, but then there's a segment missing between this and this because the sequence numbers jump. So if the sequence numbers jump, Wireshark will be able to say, hey, well, you sent me this sequence, this sequence, and then you didn't send me one, so I'm going to mark it. So it marked it here. Now, what happens in TCP when you don't receive the sequence you think you're going to get? So if I'm being sent 1, 2, 3, and then 5, well, I'm looking for 4 because 4 is the one that's the next in order. So what I'm going to do is I'm going to send duplicate acknowledgements of 3 back to the sender to say, hey, you sent me 1, 2, 3, and you didn't send me 4, so send me 4. So I'm going to send duplicate acknowledgement, and I'm going to send the duplicate acknowledgement continuously until they actually resend the piece that I missed. So you can see here, I did duplicate ACK 29 number 1. That's going to, or from me to the destination. The destination says, okay, I'll send it. Me to the destination says, okay. Me to the destination. You can see Wireshark actually numbers the duplicate ACKs. Okay. So from here to here, we're sending duplicate acknowledgements to the other side. Now, if I look at the time, we can get a sense of what's going on. So, so I send this duplicate ACK to the other side. I get acknowledgement for that about 20 milliseconds later, right? So it's 599 or 599 milliseconds to 619 milliseconds, so around 20 milliseconds later. And that is kind of in line with what we saw for the round trip time. We thought it was about 15 milliseconds. It's around 20 for this one. Same thing here. Duplicate ACK number 2, acknowledgement. Now this is a faster retransmission. You can see here it's about 6 milliseconds. Okay, so still could probably be on the internet, but faster. In this case, we have another one, duplicate ACK number 3, and we see it went just about 18, 17 milliseconds. 4, 5. So each of these is telling the sender, hey, you missed something, send it back to me. And then what we see is finally the sender here does a fast retransmission. And what fast retransmission is the fast retransmission is the sender saying, hey, okay, here's 4. We're good. Here's number 4. Stop bothering me about it. But it took quite a long time to do that, right? And the stream is not going to go forward. So if you're downloading something, for example, from this point here until you get caught up and get the correct segment, nothing is going to happen in the stream. So you can see, let's look at the timings. 12:38:04, 59, okay? That all the way to 12:38:04, 68. So that is something like 84 milliseconds, okay? Say almost 100 milliseconds before the stream continues. That might not seem like a lot to you. But if this happens repeatedly, like this pattern where you're waiting for 100 milliseconds for the stream pauses, you have a gap in the stream and you have to wait for 100 milliseconds for it to go again, that's going to overall, it's going to kill your throughput. And this is why packet loss is so bad with TCP, is because TCP is stateful. You need to fill the holes in the stream. And if you don't, you have to wait for the sender and the receiver to resync before you can keep moving. So we see this pattern, okay? So the pattern would appear as if remember, we are 1980. We are receiving data. We do not receive something from the destination. So presumably, if I go back to my diagram, okay, presumably the data is coming from, let's say the destination is out here, right? And it comes in this way to me. So at some point, something between here and here is lost. So inbound to my router, into my switch, into here, and then also all the components on the internet, some packet is lost. It doesn't get to me, and then I start complaining about it, saying, hey, server on the internet, you didn't send me a packet. And that is what's going on here. The question is that a repeatable pattern? Because if it's a repeatable pattern, then we could potentially say there's something that is systemic that is causing that behavior, versus like maybe just the packet was lost because, there was a burst of traffic, which happens all the time on the internet and on private networks. The question is whether or not that's repeatable. So let's go see if that is actually the same pattern that hits us again. Okay, so let's look down to this next block of black here in Wireshark. And let's see if it's the same thing. Okay, so look at this pattern here. Okay, let's go up a bit. Previous segment not captured. Who's saying it? So 93A1, which is the remote server, is telling me, or is sending a packet to me, and I'm saying, hey, there's a packet missing between the last one you sent. Then I, 19.8E, am starting to send dupacks. And I send dupacks again and again and again. The same pattern goes out to dupack number 6. And then finally, the remote web server 93A1 sends that as a fast retransmission, and I can continue my stream. Now again, there's the delta here. In this case, it's about 76 milliseconds. So again, we're at around 80, to 100 milliseconds of delay just for that one packet missed. You think about that. One packet missed is almost 1/10 of a second off of your stream, right? Of time you have to wait and you can't transfer data. So let's do one more verification to see if that's happening again. So let's see what happens here. Previous segment not captured, same thing. Okay, it's a segment from the remote web server to me. Wireshark detects that there's a gap between here and here. It says previous segment not captured. I, meaning the laptop, starts sending dupacks, 19.8E, send it to 93A1. That goes on till a fast retransmission. So, and that costs me about 88 milliseconds. So, again, what this is pointing to is that in the direction of me, or from the server to me, there is a packet that's being lost that I'm not receiving. And that I have to constantly be going out to the server on the internet and telling it that, hey, you're not sending me the packet. Please send it again. And every time I have to stop for that, it's going to stop all the data transfer that we're doing. Okay, so that's why when I mentioned 3% packet loss is bad, it's because one packet can stop this whole stream. Now, I'm not going to do every one of these, but I'm fairly certain it's going to be the same pattern. I can go way down, and I can look at, say this one here. It's the exact same thing. Dupacks are coming from me. Okay, so what I'm going to surmise from that is that it looks like systemic, because it's happening repeatedly. Packet loss inbound from remote server, possibly on internet, to my laptop. Okay, and that continues throughout. So this stream, whatever you're downloading from this remote server, is going to be horrible because it's going to be doing this constantly. So this is, my gut is this is likely the problem this person's having. Let's dig in a little bit more and see if we can find some more detail on maybe what they're trying to do and if this is unique to this stream or if it's actually happening to all the traffic this user has. All right, so we know we have some kind of systemic packet loss. We know the direction of it is likely inbound from the remote web server or remote server, wherever it is, if it's on the web or on another network, coming into my PC. Let's dig out a little bit more information. So first thing I want to know is maybe what is the make or model of the remote side of this remote server, or whether or not it's actually a router. So what I'm going to do is I'm going to click on that packet. The source of this is the remote server 9381 or 93A1. I'm going to look at layer 2. Let's close this off. Layer 2. The source is here, which is this MAC address here. Now, Wireshark generally will actually try to identify what that manufacturer is, so you can have a sense of, is it a PC, is it a IoT device, is it whatever. It doesn't here, so what I'm going to do is can't copy value. I'm going to come here. I look up, and I'm going to see, oh, no matches. So what OUI lookup is actually trying to identify the first three or the first 6 digits in the MAC address is unique to the vendor, and then the last 3 or the last 6 are unique to the device. So in this case, it doesn't actually have a lookup for it. So we don't know exactly what that device is. Let's see if we can find anything else about what that device is doing. So what I want to do is actually just look at all traffic to that device. You can see most of it is actually to my PC. Let's do it this way though. Let's go back. I'm going to do, instead of doing this, I'm going to do and not my PC address. Because what this is going to do is tell me what other traffic is this thing generating that is not part of not part of this conversation to me. None. So there's no broadcasts. If I saw something here, it may mean that this device is actually on my network, because if this device was generating broadcast messages, they would not be directed directly at my IP address. They'd be broadcasted to every IP address, the broadcast address, and therefore I would actually see evidence. So this here is evidence that the device is actually not on the local LAN. So I'm going to say, because all traffic is to my IP, likely remote address of 9381 is not on the LAN. Okay, good. So let's look at some other conversations now. So I'm going to do IP dot version equals 4. I'm going to take away IPv6. So I'm going to look at IPv4. So we have some other communication going on here. We have some DNS traffic. Looks like, let's just verify that. Now it looks like they've got UDP truncated, which may mean that they didn't take full-size captures. They may have taken only captures of headers, which is common practice if you don't want to display any real data. So I'm assuming though that's going to be DNS, but we can't actually inspect the DNS. That's fine. Let's look at some other things. Got some regular TCP. Now, what's interesting is that I actually see retransmissions for traffic that's not IPv6 and not part of this conversation. So what I want to do is I want to look at a couple things here. I want to do tcp.analysis.retransmission. And you could see that most of this by eye test looks like it's retransmissions to this conversation we were looking at earlier. But there are some retransmissions to other addresses as well, right? And the addresses in question look like they potentially could be on the internet. So let's do this. Let's take the IP address of the laptop. I'm going to do retransmission and not IPv6 dot address this. So what I'm saying here is that I want to look at all TCP retransmissions that are not, actually, wrong address. I'm going to say all IPv6 retransmissions that are not to this IP address, which is that remote web server. And what this is going to tell me, if I go back to my diagram, is, oh, it's gone. There it is. What this is going to tell me if those retransmissions are specific to the remote web server that I'm talking to that seem to have a lot of problems, or is it actually systemic that's affecting everything coming into my network? So I'm going to do IPv6. I'm going to take this address. I'm going to copy value. I'm going to delete this. And sure enough, I do see some retransmissions to addresses other than that one destination address. And as it happens, those retransmissions look like, for the most part, they're to external IP addresses, right? So IPv6 externals and IPv4 public addresses. So I would have loved to have a capture that had more traffic to other IP addresses in there. However, with the limited traffic I have, what I could potentially say is, looks like TCP retransmissions to other addresses on the internet, implying a systemic issue for all traffic into the LAN. Okay? Now, again, if we had more of this traffic as a sample and I said, okay, I'll do the analysis on several different public IP addresses and we're seeing the same kind of packet loss and retransmission behavior, then we could look at it and say, well, that's something systemic. It's not just specific to one web server. But in this case, it looks like it is potentially systemic. Would like to have some more traffic. All right, now let's just round it off. See if there's anything else in here that's of interest. I like to just scroll through. Most of this is this one conversation that we've looked at. Let me see if I can actually get rid of that. So what I'm going to do here, I'm just going to, this remote web, I can't negative out my own IP address because I want to look at my own traffic. What I can do is negative out the IP address of that remote web server and see what else is up. So let's do this. Okay, so this is all other traffic except for, or besides the traffic to 9381. And let's see what we can see. Got a little bit of TCP, ports 443. Looks like most of it's TLS. Again, there's some traffic. Oh, what's this? There's multicast traffic. This may be a protocol like SSDP or something like that, but we can. It's a truncated capture, meaning that we don't have the full size, so we can't see the payloads. What else do we see? That's about it. Oh, we have some ARP, so address resolution protocol. We see that there's some kind of Samsung device, E2A9. Is that an iMac address I have? Nope. It's ARPing for who has 121.9, and is that us? It is us. 6802 is us as well. So it's saying 10.86.61.205. What's interesting about this, okay, 1086 is a private address. Our address is 192.168, which is also a private address. Normally, if this is a home network, then you would have only one subnet, one private subnet, and then everything else would be public. So you'd only see private addresses of 192.168 or 172.16 something, and then everything else would be public. But in this case, you see that something is ARPing for an address, and they're saying I have an address of 1086, but you're on 192.168, and then I'm going to reply to you with ARP. So you could do some research on ARP, but what's curious about this is usually if you're ARPing on a subnet, the two hosts need to be in the same layer 2 domain, meaning when I send this ARP, I'm expecting that everything else on this that I'm ARPing to is going to be in the 192.168 subnet. So maybe if this is a /24, 192.168.121.0/24, and that this would say like that, tell 192.168.121.5 or whatever. I'm seeing ARPs on two different private subnets is weird. This doesn't actually make sense. So either the subnetting of this LAN is really messed up for some reason, or something else is going on, because this shouldn't actually happen. So I don't know if this is related to this issue, because really, if ARP was broken, you wouldn't see any traffic transmitted in the first place. But this may lead to a misconfiguration of some other kind on that LAN, where you have devices of two different IP subnets on the same layer 2 domain, which is a big no-no. Okay, so just a note, but not necessarily related to this the overall problem they're having. And last little look through. Oh, ARP again. Now this is what I mean with a better ARP, but again, who's doing the subnetting? So 192.168.121.9, tell 192.168.152.199. So it isn't necessarily a problem, because you could have a subnet that is 192.168/16, which means that 192.168 could be standard and then everything else is variable after that. But it doesn't really go like that. Usually when you do 192.168, you do /24s, meaning you have the first 3 octets are standard. So again, this points to some kind of weirdness with the subnetting on this LAN. So just something to note. Some more DNS, more IPv6. And lastly, again, the same weirdness, right? An address on a different subnet, or at least what is usually a different subnet, is ARPing for an address on a different subnet. So as far as I can tell, looking at this problem, to summarize, it looks as though we have some systemic inbound packet loss from a remote server, possibly on the internet, but we don't have that detail. But based on the round trip time, it looks like it's on the internet to my laptop. Because, as I mentioned, that the traffic from 9381 is to my IP is likely not on the LAN, meaning I'm not seeing things like ARPs or broadcasts from 9381. So you don't see those things unless the host is on your subnet in your local LAN, right? Looks like the retransmissions are to other addresses as well, from other addresses on the internet, which would imply a systemic issue coming in, as opposed to just an issue with one specific web server on the internet. And finally, weird ARPs between different subnets, maybe local IP addressing issue. So if I were to guess what's happening, I would guess that either there is some kind of systemic issue in the cabling, from the router to the switch, or if you don't have a switch, from the router to your PC. If, say, this PC is not having the issue, but this PC is having the issue, then you're looking at like this segment here. If both PCs are having the issue, then you're looking at this segment here. If, again, you don't have a switch and these things are connected directly into the router, then you're probably looking at a cable that's upstream. Say you have the cable coming from the ISP, the cable, the coaxial cable, or the fiber coming into the router. You could have like oversubscription, meaning that overutilization, because if you're downloading too much, like say this person here is just downloading a ton of movies, and you're trying to download at the same time, then inbound, this interface here is going to get overloaded. You're also going to have the interface that is upstream at the ISP. that's where they throttle you down to a certain speed, right? So if your ISP is setting you to say, 100 megabit per second, they're doing it in their network at a certain point, at a certain router, which is, the throttle point, and they set your speed. So if you're trying to push too much data downstream, meaning from the server down into your network, and you're only set to 100 megabit per second or some limit, then you'll see packet loss in the inbound direction, which we see, and then you'll see the same kind of retransmission. Now, normally with that, you could tell it pretty quickly because you'll just walk around your house and you know that people are downloading information. You're downloading too much. So if you're seeing this scenario at a time when you're not downloading a lot of data, so say there's no utilization on your network and you're still seeing that loss, that would imply more of a cabling issue, hardware issue, because it's not a discard thing. You're not hitting 100 your capacity and then your router is discarding traffic above that. You're just downloading a regular rate of traffic and that's getting dropped. So all of those things are possible. Again, this person didn't actually put more data into this. What I hope you got from this analysis is just kind of a real world view of how I would go through and analyze a capture without any prior information, or at least a very little amount of prior information, and some of the tips and tricks that you can use to kind of glean as much information you can from a capture. That's it for this video. I hope you found this video useful. If so, please like and subscribe. Also, if you have an issue that you're working on and you would like to review the capture on the channel or get some advice, feel free to post a link to it below with a description, and I'll get back to you as soon as I can. Until next time.